In this video, we will be discussing projectile motion and how it relates to the physics that we're going to be doing. So to begin, in our everyday lives, you might have heard of what projectile motion might be, but how it works and what it's used for in physics, you might not exactly know. Well, what is a projectile? A projectile is an object, sorry about that, is an object that moves on a curved path due to gravity. So it's anything that's like moves on a curved path due to gravity. Now this could be falling, or maybe it's thrown. Maybe like you have a soccer ball, you kick it, that's a projectile. Anything like that can be with projectile motion. But projectile motion, the important thing to know about projectile motion is that the horizontal, which is the x, and vertical, which is the y, are split up or another word is they're independent of each other. When we're working in projectile motion, we're going to be using a lot of components because we have to look at the horizontal motion and the vertical motion because they're separate and independent when we're working with them. So the way to understand how projectile motion can be applied, we're going to use a lot of the equations that we used for kinematics before, but similar to how we were talking about in the last video of using components like x and y for displacement, we're going to be using a lot of x and y components with kinematics. So we're going to be focusing a lot on subscripts and things of that nature. So let's get into the questions, and we'll try to solve through using some of the equations. Okay, so I have the first question pulled up here, and it says a soccer player running on a level playing field kicks a soccer ball with a velocity of 9.4 meters per second at an angle of 40 degrees above the horizontal. Determine the soccer ball's time of flight. So the part A, we're looking for time of flight. So let's go given, and let's look at what we have. So we know that it's kicked at 9.4 meters per second at an angle of 40 degrees above the horizontal. So what does this really mean? So let's try to maybe draw a diagram that could help us. So this is a soccer ball. Person right here gives it a little kick, and now the soccer ball is going something like this. This is what's going to end up happening to the soccer ball. So this theta right here is assumed to be 40 degrees, right? So let's try to draw out a little diagram to see what we can have. So let's put a right angle triangle here, because you know it's above the horizontal, which means that it's basically going to go right and then up. So we can set these as our positives because we're going right and up. And we can put theta right there. So the reason we drew a triangle is because even if we draw a triangle here, we can get a simple right angle triangle, similar to how we broke up our previous examples into components. So let's put right and up as positive because it says above the horizontal. Whenever it says above the horizontal, you can assume that you're going to have to draw a right angle triangle because you're going above the vertical, above the horizontal right here. So now that we have this, we know that the velocity is 9.4 meters per second. And at an angle, so it says at an angle. So the velocity isn't just straight to the horizontal like this or straight vertical like this. It's at an angle, right? So we know our velocity is going to be right on the hypotenuse. So it's going to be, our v is going to be 9.4 meters per second, correct? And we can label that as our v1. Then we know that our we have a vx, we have a vy, and we have a vx. You don't necessarily need to include a vector here because we already defined the direction in our triangle, so we don't need to add vectors. But we know that vx, we're just going to use simple trig. We know that this is going to be the opposite of the reference angle because this right here is opposite, and then vx is going to be adjacent. So we know that adjacent is just going to be cos theta multiplied by v1. And then we know that vy is just going to be sine theta multiplied by v1. And we know that this is going to be sine because vy is opposite the reference angle, and we know vx is going to be cos because vx is adjacent to the reference angle. Now that we have all that down, we have vx and vy, and we know this is going to be 1 and 1. These are the initial. We don't know the finals, but we can go to the next part. The next thing that we know is the acceleration in the y direction. And the acceleration in the y direction is always going to be 9.80 meters per second squared. Why do we know this, or why can we kind of assume this? Well, if we kick a ball up here, it's going to be accelerating downwards constantly because of gravity, right? And that acceleration downwards in the y direction, in the vertical, is because of gravity. So we can assume that the acceleration on the y is going to be 9.80 meters per second squared. But that's going to be negative. Why, you may ask, is it negative? Well, because up here we defined up to be positive. So we have to make down negative. So now we have v1y, we have vx, we have velocity of vx1, and we have these two things. The important thing to know about velocity in the x direction in specific is that velocity in the x direction is constant. So you won't have a vx1 or vx2. You'll only have velocity in the x. Why is this? Well, let's say you're a person right here and you throw a football. The football in the x direction the velocity is going to remain constant, right? If you throw from this end of the field all the way to here, the x is going to be constant. What changes is the velocity in the y. It may go up, down, but in the x, it's constant. That's why our velocity in the x is always constant. So our vx is going to equal our vx1 is going to equal our vx2. But our vy, our velocity in the y, is not going to equal the velocity of our final. So that's something we have to keep in mind when we're doing this problem. And any kinematics problem, because velocity in the x is always going to be constant. So now that we have all this, let's see if we're missing anything from our given. It appears that's all really what we're given. So let's try to figure out what we can do here. So we can go required to find, and what we're looking for is the time, right? The time of flight. So let's see what we can do. So let's say we want to work in one direction, right? We can use our kinematics equations. Now that we're in 2 dimensions, we can use them. We're going to use the same equations, but use delta dx is equal to 1/2. Sorry, let me rewrite that a little nicer. Let's say we use the same equations that we were using before. Delta d is equal to 1/2 a delta t squared plus v1 delta t. Let's say we use the same equation that we used from before. Well, the issue that comes from these equations is, first of all, these don't have a specific direction. We don't know if these are all in the horizontal or all in the vertical. So to determine which direction we're working in, we have to set that. Remember at the top right here, we discussed that the horizontal and the vertical are independent of each other. You can't mix x's and y's. We can't mix this vertical acceleration with this horizontal velocity. Those can't mix. You have to keep them independent. So let's try to make this delta d. We have to make everything in this equation in the x direction. So how are we going to do that? We need to put delta dx, and then ax, and then time, and then vx. The only thing about time is the only constant. No matter if you're holding a ball and you push it off a ledge and it falls, the velocity in the x and y may be different, but the time that it hits the ground will be the same regardless of the velocities, right? The time it hits the ground will be the same no matter what you look at. That's something important to keep in mind. So here, when we're looking at this question, and now we have this. Well, if we look in the x direction, we're looking for time, right? So we're looking for delta d. We're looking for delta t. Well, a problem arises. We don't know what t is, but we also don't know, we also don't know what ax is, and we don't know what delta d is. So we have too many unknowns in this specific problem for it to really be useful to us. So let's turn, whenever you can do something in one direction, turn to the other direction. So instead of vertical, instead of horizontal, let's go vertical. So delta dy is equal to 1/2 ay delta t squared plus vy delta t. Now we made sure to keep our y's, all our directions the same. We're working in the vertical. So we're going to use only our vertical knowns. So we know that the vy one, should put a 1. And we know all these things are known. Now, the thing about this question is, something that you can pick up on is, oftentimes when you're working in physics, as you're doing the question, you'll notice that you're able to see pieces of the given that you may not have seen before. And for this question in particular, we can try to think back and we're like, okay, we don't know what delta dy is, but let's hypothesize what it could be. And what I mean by that is, if we make our diagram again, right, and we have a person here, the stick figure, and he kicks the soccer ball, right? Well, if you look at what delta d means, delta d is just like what the displacement is, right? What the displacement of the ball is. And if we look in the y direction, so that means a vertical displacement, up and down displacement, how much it changed. Well, vertical displacement of a ball that gets kicked, it may have this vertical displacement in the middle right here, but when it lands back on the ground, if it started on the ground and lands on the ground, that means it vertically displaced 0, right? So if it vertically displaced 0, that means our delta dy is equal to 0 because it didn't displace at all. So we can put delta dy is equal to 0. We can go back and modify our given as we find stuff out. So now that we know delta dy is 0, one of our terms dropped out, which means we don't have to use the quadratic formula. So now we can just go 0 is equal to 1/2 ay delta t squared plus vy delta t. Now that we have this, now we know we want to get delta t by itself, right? That's one of the first things we want to do. We want to get delta t by itself and try to work from there. So how are we going to do this? Well, we can try to minus from here, minus over this term and bring it here, but that's going to get a little messy, and there's a little bit easier of a way to do it. Well, you can notice that there's a delta t here and a delta t here. Well, that's the same as if we had an ax plus bx, right? We have x in both terms. So what can we do? We can factor them out. So for this delta t, we can actually factor out the delta t. We can write this as delta t out here, right? 1/2 ay plus Vy, and, pardon me, I forgot a delta t here. So, oops, I'll just rewrite that. It's ay delta t plus vy. And now we have our new equation. Now we can just divide by, now we want to get rid of this delta t up front, right? So if we divide by delta t, if we divide delta t here, we can just go delta t, so these will cancel, and if we divide 0 by delta t, anything divided by 0 is just 0. So 0 is equal to 1/2 ay delta t. Don't forget your vector signs. Clearly I was dropping them, but it's always important to double check your work and make sure you're not dropping any vectors because they will catch up to you. But 1/2 ay delta t plus vy1. Now that we have this, now it's a little easier to just get delta t by itself, right? We know that we can just subtract this term over. So we can go minus vy and bring this term to the left. So we have negative vy1 is equal to 1/2 ay delta t. Now we want to get rid of the 1/2, so we can times by 2. And now we're just left with the ay here. So we can divide by ay because what's holding it together is multiplication. So we have negative vy1 times by 2 divided by ay is equal to delta t. Now you may be looking at this and wondering, but now we're going to get a negative answer, so we must have done something wrong. Well, actually, after we keep going through this, you'll notice that our answer isn't negative. So let's just continue here. So now we can go straight into our solution. We know that it's going to be negative v1y. But what is v1y? We go back here, v1y is sine theta times v1. So sine, and theta was 40 degrees, times v1, which was 9.4 meters per second. And we're just going to multiply this all by 2, and we're going to divide by negative 9.80 meters per second. Why negative again, you wonder? Well, we set up as positive. So if the ball, if the ay is actually just gravity and gravity goes downward, well, that's going to be negative. So negative, and that is all equal to t. And if you punch that into your calculator, these negatives will cancel out, and you will be left with delta t equaling to 1.2 seconds. And that's your answer for part A. Part B asks, what is the range, right? We have to find the range. Well, if you remember what we were previously talking about Vx being constant, right? Like it's constantly, just like I said, if you threw a football this way, the football's speed and the x would be the same. And the y, it could change though. The y, it changes, but in the x, the speed is the same. So this final is equal to the initial, right? Or v2, like vx is equal to v2x, which is equal to v1x, right? It doesn't really matter. They're all equal. That's the important part. So how does this help us? Well, if you remember our equation for velocity, velocity is equal to delta d over delta t. And when we're looking for range, we know that the range is going to be, if we have a range of soccer field like this, if this is one part and then all the way to the end here is the range of it, this is all technically a distance or a displacement, right? So we're looking for delta d. And in this question, up here, we already calculated what the time is, 1.2 seconds. So if we multiply simply by time, we'll be able to isolate for delta d. So Vx times delta t is equal to delta d. right here we can go straight into our solution. Our solution is going to be, this we can call our analysis, but it's more like an explanation. But our Vx is going to be, again, cos times V1. So we need to go cos theta, which is, so cos 40 degrees times V1, which is 9.4 meters per second, and just multiply that by delta t, which is 1.2 seconds. And that ends up being, so cos 40 times 9.4 times 1.2 ends up giving you 8.6 meters. So that means delta d x, remember, you have to put your x's because we're talking about specific components about this. So delta dx is equal to 8.6 meters. And that is your final answer. The last part we're going to look at today is trying to find the maximum height for this object. So to try to determine what the maximum height of the ball that was kicked was, there's a few strategies that we can try to look at and evaluate, right? Some that come back from grade 10. But if we think back to our soccer player here, kicking the ball, and this is the field, right? He kicks the ball. Well, something that we can take note of is that when someone kicks a ball and it hits a maximum height, right here, what happens to the speed of something at a maximum height? Well, let's say you throw up your pencil in the air. For a split second, before it starts falling back to the ground, it stops, right? For a split second with anything, it changes direction. If you throw your a soccer ball in the air, for a split second before it hits the ground, before it starts falling back down, its speed is 0. How can that help us? Well, that actually gives us the final speed for its time in the air. So if we look here and we think, okay, what is our given now? Well, our given is that we have v1y, or vy1. We have this, which is just equal to sine theta times v1, correct? We have that. Now, what else do we need? Well, now we have v2, which is just equal to 0, because at the max height, it stops for a split second, which means v2 is equal to 0. Okay, now we have that as well. What else? Well, we also know that we're trying to find, technically, our required to find is, when it says max height, we're looking for really delta d, right? Delta dy, the distance in the y direction. Okay, we know that. We know that our ay is going to be 9.80 meters per second squared. Now we can set, again, right and up to equal positive, so it would be negative 9.80 meters per second squared. But now we're getting somewhere, right? We have a few different variables that we can work with. So if you think back to one of our equations of motions, or kinematics equations that we've found, one of them was v2 squared is equal to v1 squared plus 2a delta d. Now, why did we choose this equation? Well, we know that this equation will work here because we have all the y components for this. We have v2y, we have v1y, we have ay, and we're looking for delta dy. We could have, if you think back, why didn't we use maybe this equation here? Well, we're looking for delta dy, which is correct. And we have ay, but we don't have, we do actually have the time now too. So you're trying to look for the maximum height though. So you don't know the height you don't know the time at the maximum height. You know the time overall, but you don't know the maximum height. You could say that you could divide it by half, and because it's a parabola, half of it, you'll know the time at the maximum height. But that's still, again, let's say our time was wrong, like up here. Maybe this time that we calculated, 1.2 seconds was wrong. If that's wrong and then you use it in a calculation to try to find the maximum height, then your new answer is wrong. This approach allows you to make less error when you're finding your answers. So let's continue. So we know that V2 y is going to be 0 because for a second it's going to drop out, right? So that's just going to be 0. So now we know 0 is equal to v1y squared plus 2ay delta dy. Now that we're here, we can try to figure out the rest of how we can proceed. We're trying to isolate for delta dy. So what are we going to do here? Well, the first thing is we can move this term over by minusing. So v1y squared, we can just move that over simply by subtracting it over. So we can go negative v1y squared is equal to 2ay delta dy. So now that we have this, we can remove these two things by dividing them out. So divide by 2 and divide by ay. And now you have negative v1y squared over 2 times ay. Now that you have this, you know that that will equal delta d. Again, you may wonder why we have a negative up top. Does that mean our answer is going to be negative? And if so, how is that possible? Well, you have to remember that, again, in this case, the answer won't be negative because our ay is negative. So the negatives will end up canceling out. So we can go straight into our solution. Our solution is going to be simply v1y. And what is v1y? Well, v1y is sine theta, so it's going to be sine 40 degrees times 9.4 meters per second divided by, oh, and remember, all of this is squared. That's an important part to remember. So squared, and it has a negative sign in front, divided by 2 times negative 9.80 meters per second squared. And that will equal delta d. Y. Remember, it's in the y direction. We're looking for the delta d in the vertical. The components are independent of each other. So now, delta dy is equal to, now the rest is just calculator work. Really just plugging in the numbers and seeing what answer you get. And for this one, you end up getting, let me just punch it in. Your delta dy ends up being 1.86 meters, which you can round off to 2 significant digits to be 1.9 meters. And that is your final answer. So to conclude, that was my video on projectile motion and kinematics. That will be my last video for this unit because next we'll be moving on to forces. The important thing to remember about kinematics and projectile motions really is to make sure you break it up into components. Components will make it a lot easier and a lot simpler. Remember, if you don't have enough information in one direction, you can always switch to the other direction. Just like here, we didn't have enough information in the x, so we went to the y. And sometimes you can use sub-in constants from all around. Like time will always be a constant, whether it's in the x or y. So you have to really just leverage around and really algebraically manipulate and play around with what you have. You have to remember certain keywords like at rest or maximum height, what the velocities are. And you have to really remember that Vx is always going to be constant. Like your Vx is going to be constant. It's a constant, right? Your velocity in the x is going to be a constant. So you can use that to your leverage, just like we used here to find a delta d. So all these things combined, you have to really just pay attention to your subscripts and to make sure you're working in the right direction. Remember, you can't mix directions either. You can't mix the x and y components. They must be separate of each other. So if you do all these things, I believe you will be successful when working with components because it is something that is tricky. And there's a lot of work that goes involved with it. It's really just about trying to pick the right equation, trying to get the right answer. And if you don't get the right answer the first time, you have to rearrange and just try again. But you have to just keep trying, and that's the best way to really approach physics as a whole. And also remember to always define your directions and make sure your negatives are in the right spots, and that you always carry through everything that you write, that your nomenclature is all right, and that you know what you're really looking for. Look at units, because that can always help you catch mistakes. And if your units are ever off, you know that you could have possibly made a mistake. Don't forget your vector signs. But that is the conclusion for my video. Thank you for watching, and remember, physics rocks.